Hi, I'm Roland Larsson, and this video is on rolling friction. So in other videos I have been discussing sliding friction and the different types of friction that occurs in a sliding contact. And in this case I will discuss rolling friction, which is a very important type of friction actually. In the contact in a railway wheel contact, in a car tire contact, and in many other rolling cases. So let's go. Before starting to discuss the mechanisms of rolling friction, I want you to sit back and think about the following questions. Why is friction so low during rolling? I mean, normally we see that the friction is very low actually. And when it is that low, how can then a train or a car stop? So stop the video for a while and think about this for a few minutes. Okay, now let's start discussing the different mechanisms of rolling friction. We start with one thing named microslip. So even if this is a rolling contact, there is some slip in the contact anyway, because most wheels are deformed because there is some load applied on the wheel, and there is a flattening of the wheel in the contact zone like this. This is maybe a little bit exaggerated if it's a train, but for a car tire road contact, it's more representative maybe. What is happening then? Well, if we put ourselves in the following the wheel, that means that the road is moving with a speed of omega r, which is the rotation speed of the wheel, and the wheel surface is also rotating with having a peripheral speed of omega r. That's the definition of rolling. But here, when the wheel surface comes into contact, the radius is suddenly becoming smaller. So that means that the speed is lower here in the contact, and still the road is moving with omega r. So there is a slip, there is a sliding friction component here, and that sliding friction component creates the rolling resistance or the rolling friction of this tire due to microslip. There is also a plastic deformation part of this one. If you think about it, you may have a wheel here. It may be a very hard wheel, and it may roll on a softer surface. This is, for example, if you're driving on a soft road, a soft dirt road or something, you continuously deform the surface, and the plastic deformation of the ground of the road is a dissipative process, and that gives rise to friction, or maybe it's more correctly in this case to talk about the rolling resistance. So that's, together with the microslip, the plastic deformation creates this rolling resistance of the wheel. Then there is also something called viscoelasticity, as you know. So some materials behave both as solid and a fluid. Well, I would say that all materials do that, but in some materials you hardly see the fluid behavior, like a metal, for example, have not that much viscoelastic behavior. Elastic deformation is not a dissipative process, so you regenerate the energy stored in the spring to 100%, but viscous deformation is a dissipative process. You don't get any energy back when you deform a fluid. So typical materials where this is playing an important role is that's elastomers and also rubbers. What you can say here is, which is important to remember, then in a viscoelastic material, force and deformation, they do not follow each other. Like in a perfectly elastic material, the deformation and the force is following each other perfectly well. But that doesn't happen in a viscoelastic material. And this viscoelastic behavior it's not constant, so it is pretty strongly dependent of the frequency of the loading and also the temperature. So these illustrations taken from Michelin literature shows the influence of the frequency, for example. So if you excite the rubber in a very high frequency, it behaves like a glass, a brittle material. While if you have a slower excitation of the material, it behaves like a rubber, more like a spring. And here, somewhere in between, it behaves very much as a viscoelastic material. The hysteresis is at its maximum. So you have both elastic and damping effects of the material. So and what has frequency to do with a tire, you may say? Well, in a tire, the tire is of course loaded at different frequencies depending on the speed you are driving at, and also the kind of nature of the topography of the road. Apart from the frequency, the material is also highly temperature dependent. So you get the same effect also depending on the temperature. At very low temperature, it behaves at the same way as at high frequencies, while at high temperature, it behaves more like in this perfectly elastic rubbery state. And somewhere in between, you have the maximum hysteresis. Actually, this is used when you design a tire for winter use, for example. This maximum should come at the operating temperatures, say below 0, for example. And the same goes for a shoe sole, I would say. So, what is happening then when you have a wheel made of something viscoelastic? Well, as I said, the deformation and the force, they don't follow each other, and the viscous deformation is dissipative, and this is occurring inside the wheel, and everywhere where you have a deformation, it doesn't follow the force maximum. So when you roll this wheel over the road surface, it deforms, and the viscous part is you are losing energy or losing power in that process, and every time you lose energy in that way, it behaves like a power loss, and it's a kind of rolling friction then, or a rolling resistance. And of course, as I said, all materials have to some degree an viscoelastic behavior, but metals internal damping is very low, so it's at least at room temperature and a little bit above that. But at higher temperatures, closer to the melting point, also metals have a viscoelastic behavior, I guess. Okay. Well, what can we do then to minimize rolling resistance? Well, we can have a very high elastic modulus. That means that you have a small deformation, and that minimizes the microslip. You may have very high hardness of the two surfaces, and that means that you don't get any plastic deformation, not of the ground, of the road, of the counter surface, not of the wheel either. You may have equally elastic surfaces. That will also give an effect of less microslip. You should then also minimize the viscoelasticity if you want to minimize rolling resistance, but maybe not if you want to minimize the braking capacity of a tire. But of course, if you're doing this, if you think about this, you should make everything of a steel, for example. But driving a bike or a car on the steel wheels will have pretty negative consequences. It will be a very bumpy journey and not as safe as using elastomer tires. Okay, but what is happening then during braking and accelerating? This is it's a little bit contradicting. You really want to have a vehicle with as low rolling resistance as possible, but as good braking and acceleration properties as possible. That means that you really want good high grip, good friction during braking and acceleration. So let's take a look of this model. It's a little bit a brush model, you may say. We can assume or pretend that the surface is made of a number of brushes or hairs like this. So these blue ones are artificial brushes. It's not a brush there in reality, but let's pretend it is a brush like this. And then let's assume that the surfaces are moving slightly at slightly different speed. So the upper surface moves a little bit faster than the lower surface here. So what is happening when we follow one brush here or one hair of the brush, then when it first comes into contact with the counter surface, the brush sticks to the counter surface, and due to adhesion forces. Then some a short moment of time later, the upper surface have been moving a little bit longer than the lower surface, but the hair is still sticking to the surface, but it has now been a little bit sheared, or some stresses have occurred in the contact between the hair and also in the hair itself, of course. And then when you keep on shearing the brush hair, you will soon reach to a position when the available friction is not high enough to keep it sticking to the lower surface, so it starts sliding. In this deformed state, it will start sliding, so now it will continue sliding through the contact as it is shown here. And it will do that until it reaches the end of the contact, and then it's released again after that. So let's translate this now to a real contact of two surfaces, two smooth surfaces in this case. What you have is the kind of Hertzian contact, or the contact pressure distribution in the contact that looks something like this. Here, when the contact starts, you have zero pressure, and then it increases to a maximum and then goes down to zero again. So, and this curve could be the available friction is then mu multiplied by p. Now, when the first position here, where the wheel is touching the road or the counter surface, it will stick. And as that point moves through the contact, the shear stress will be bigger and bigger depending on the speed difference here. But it will increase, and eventually it will reach the available friction level here, mu multiplied by p. And when it does, it starts sliding. So from that point until the very end, the surfaces are sliding. They are not sticking together anymore. So for that reason, in a rolling contact, you have two zones. You have a stick zone and a slip zone. So that's maybe something you don't think about when you drive your bike or your car. So actually this part of the tire is not is sticking, but this one is slipping. And that means also that the sooner you can reach the available friction, the more friction you get. So actually the more grip you want, the more sliding you will need. So to get just before gross sliding, that's you're skidding with the whole wheel, then you don't have any sticking at all. The sticking keeps you prevents the wheel to start sliding completely. But as soon as you have sliding all the way here, then the wheel will stop rotating and you will have just a sliding wheel. But that's not what you want. But before that happens, you really want to have as big slip zone as possible in order to get as high grip as possible. So that's a little bit amazing that in order to have as good braking and acceleration, you should have more slip. It depends then also the speed difference, of course. The bigger the speed difference is, the sooner you enter the full sliding zone here. And that looks something like this then. If you have no speed difference, there is a very small friction. It's just a microslip and such phenomena. It's a rolling friction then. But then when you increase the speed difference, the friction goes up, and eventually when you have full sliding, you end up with mu multiplied by n, of course. With thermal effects, this will go down a little bit because then you haven't got as good grip, and you change the mu itself, and you change the behavior of if it's a tire, for example, you change the properties of the rubber itself. Let's discuss the friction mechanisms for tires then in a little bit more detail. The mechanisms are of course the hysteresis effect, as we have been discussing, is very important for tire friction, and that's the reason why you're using rubber as the material for the tires, of course. So since the deformation and the force or contact pressure doesn't really follow each other, you get an unsymmetrical pressure distribution around the asperities of the road here, and that will give you a friction effect when you start sliding the wheel. But there are also other effects. You also have adhesive effects, so you have some adhesion in between the surfaces. If you then have some water film here, you reduce that adhesion. So that's one of the reasons why you lose grip when the road is becoming wet. And this is, of course, a very, very kind of simplified picture of the road surface, and there is actually roughness on the road here. So the micro roughness will actually break through the water films if there are any, and that will create some extra friction actually. So that's good. So it depends on the type of material you're using to make the road. If you have if the rocks are very smooth or not. If they are very smooth, you will get a road with less good friction, I would say. Important to remember is, of course, that it's the rubber material's viscoelastic behavior is frequency dependent and temperature dependent. So it will, the same wheel, the same rubber, the same tire is not as good at +30 as at -30. it depends very much on the type of rubber you're using in the wheel, in the tire. So winter tires made for Nordic climate, minus 10 or so, they are made of a softer rubber than the summer tires. And this speed dependence is also a problem. So if you drive faster, you can think about it. You can think about it. What is happening if you drive faster and faster? Will the grip increase or will it decrease? This is an illustration taken from Michelin, and it shows the same thing as we discussed before about the sliding and the sticking phase of a braking or accelerating wheel. So here you can see that the vehicle is moving in this direction, so that means that the tire, the first encounter of the thread block is here, and then we follow the same thread block through the contact here. So here it sticks, here it starts to be deformed more and more because the road is moving faster, and eventually we reach the limit of sliding friction or sticking behavior here, and from here and until the very end of the contact, the thread block is sliding in contact with the road. So so it doesn't really matter if you are braking or accelerating. It's just a deformation in the other direction if you do that. So you get a behavior that looks something like this. The friction varies like this. So we call this the mu slip curve. So here you have braking and here you have driving, and G is just the slippage rate. If you depends on, it can go to infinite because you are using if the road speed is set to 0. It's a matter of definition here. Okay, so that's a good illustration of tire friction. And then taking also into account that there, apart from the hysteresis effect, you also have a water effect of water. So if you have a perfect rubber and dry, no water available, the friction coefficient will be very high. It's well above 1. But as soon as you get some damp or some water on the surface, you get still with some roughness on the road, you reduce the friction very much. And if you also make the road very smooth, like on a worn road, then you have the road surface has been made very smooth, plus the water effect that you don't have any adhesion. Then you may come down to a friction coefficient of as low as 0.2. And then also if you add some ice or snow and make it very slippery, then you may have a friction coefficient as low as 0.01 or so, and that is a really dangerous situation. Then the wheels will just slide, and the whole vehicle is just skidding, and you may lose your grip completely and leave the road in a bend or so. So that is short about rolling friction. I hope that is clear enough for you to understand why there is why there is so low friction when you have pure rolling, but still that it's possible to get relatively high friction when you start braking. Thank you very much.